In this section, we will continue to see the concept of recursion. So first, let us revise the previous concept. That is, we have seen how to write a recursive function to calculate the factorial of a given number, where the number is passed as a parameter to the function. Let us run this example once again. So what have we done here? Suppose we are calling a function factorial by passing the parameter n. Suppose n is equal to initially 3. So we want to find the factorial of 3. First, we'll compare 3 with 0 if condition is not satisfied. So we will call 3 into factorial of 3 minus 1, that is 2. Right? And this way we will progress provided that n is not equal to 0. Once n becomes equal to 0, we have to return 1 and then go in the reverse order upward, or it is also called as to backtrack. Okay, so we'll solve this example once again now as a part of revision. So suppose your main function, initially it will call the function f, suppose. Okay, in your main, you have certain statements. Then one among them is a function called to the factorial function. And after that, you may have some other statements. Okay. So the main will call the function. But who calls the main? Do you remember? The operating system will call the main. So within the operating system, there will be a call to the main function of this particular program. And then the main of this program will call the function factorial. And within the function factorial, we will call the same function factorial multiple times. And this will continue as long as we don't reach the base case. Once we reach the base case, the value will be returned to the main. And then main, the control will return from the main to the operating system. Right? So from operating system to the main, from main to the particular function, then we'll come back to the main and then back to the operating system. Assuming that the main has made the call to the function f. So now for the function f, we have passed the parameter value, suppose 3. So for this particular function call, first I will compare 3 with 0. If condition is violated, not satisfied, so what will happen? Else part will get executed. What is there in the else part? We need to find the answer of n, that is 3, into f of n minus 1, that is 3 minus 1, that is 2. Now here again a function call is made, so control will jump to the definition part, but passing the parameter value as 2. So from here control will jump to the definition part, for which the parameter is 2. And then again the definition will get executed for the parameter 2. So what will happen? I will compare the n value, which is now 2. Now n is equal to what? 2 for this particular function call. I will compare 2 with what? 0. If condition not satisfied, else part will get executed. What will happen? 2 into f of 2 minus 1, that is 1. Again a function call is encountered, so I will again go to the definition part, but this time with the parameter n equal to 1. Again we have to repeat the statements within the definition of this same function. What we have to do? Compare 1 with 0. If condition again not satisfied, else part executed. What is in the else part? You have to find 1 into factorial of 0. Again a function call. So we'll jump to the definition part by passing the value of n as 0 now. Again we'll compare. This time 0, we have to compare with 0 if condition satisfied. So what will happen? I have to simply return the value 1. Where this 1 will get returned? This value 1 will get returned to the previous function at the call. This function with the parameter 0 has been called from the previous function, right? This function with the parameter 0 has been called from the previous function. So there I will return. This value 1 should return over here at this call. So the value of the function call with the parameter 0. The value of the function call with the parameter 0 is 1. Whatever value is returned, that will come in place of this. So now what I have to do? The value of this function call with the parameter pass 0 is 1. So 1 into 1 is nothing but 1. Okay. And this one has to now be returned to the previous function, which had called this function. So this one will get returned here. So 2 into 1 has to be computed, which is 2. This 2 will be returned to the previous function wherever it was the call. So 3 into 2. 3 into 2 is 6. Finally, this 6 will be returned to the function call whenever it was called for the first time. Where was it called for the first time? Within the main. So within the main function, suppose you are writing int a equal to f of 3. What is the value of f of 3 function call? 2. So f of 3 will get replaced with 2. Now a is equal to 2 and you can print the value of a. Okay. And then finally, the main function is also executed completely. So it will return back to the operating system, which has called this main. Okay, I hope you have understood the control transfer for the factorial program. So we have seen the difference between iteration and recursion also. Whatever you write within a loop, simply replace it by putting that same statement, that same set of statements within the loop should be put inside a function and call that function within itself repeatedly. And you can exit with the help of the base case. If base case is not executed, what you execute? The recursive case. So we have seen that how the memory will respond, how we can know that where we have to return using the activation record. The main two fields in the activation record is the control link and the access link. Control link we have already discussed. It will store the address to which the control should return after executing the particular function. I repeat, control link acts as a pointer. That means it will store the address of the location within the function which had called it. Okay, for example, initially, suppose I'm calling the main function. Within the main, I'm calling a function f1. Then I'm calling a function f2. And then finally, end of the program. So what will happen? Within the stack, the activation records will be there. Okay. Memory will be allocated to execute these functions, as well as there will be activation record for each of the functions. So initially, operating system calls the main. So activation record of main will be there in the stack. Okay, this is the activation record for the main function. Now it has a particular control link and an access link. Access link we have to still discuss. What will be the control link? Now main has been called by the operating system. So once we return from the main, where we have to return back? To the function which calls the main, or to the system which calls the main. Who has called the main? Operating system. So when we return from the main, we have to go back to whoever has called it. Who has called it? Operating system. So from the main, we will return back to the operating system. So the control link of the main will store the address of the location within the operating system to which the control has to return. So it will be a location within the operating system. Control link will store the corresponding address. Now, after executing some statements in main, I need to call this function f1. So control will jump to the definition part of f1, and memory will be allocated to f1, and its activation record will also be there in the stack. Now this f1, all the statements will get executed. Now how do I know where I have to return? With the help of the control link field of the activation record of f1 function. Who has called f1? Main has called. So where I have to return after executing f1? I have to return to the main. So the control link will have the address of the location within the main to which I need to return. Now where do I need to return? At this call. I need to return at this particular call after executing f1. So the corresponding address over here will be the value of the control link or the control field. So this control link stores the address of a location to which I need to return, and this address is surely within the main. So control link will help you to return back to the main. Okay. So I have returned back to the main. Now what I'm doing, I have to execute function F2. Okay. Once I return to the main, the memory which was allocated for F1 will be deleted. So this will not exist. Okay. And just above the main or wherever you find the vacant place, you have to create the activation record for F2 function, and also memory will be allocated for F2 function over here. Okay, in place of F1, now you can have the memory allocation for F2. I execute all the statements within F2. Control link of F2 will be for a location within the main, because main has called F2, so I have to return back to the main. So control link will help the system, or it will help the control to reach back to the main. Now there are no more statements within the main. So whoever has called main, I have to return there. The control should return to the person who has called the main function. Who has called main? Operating system. So control will return back to the operating system. So the control link of main is pointing to a location within operating system, as we can see here. So I'll go back to the operating system, and memory will be deallocated for the main as well. So finally stack will be empty. Okay, this was for the normal function calls where recursion concept has not been used. Same is the case for recursion. Okay, so in recursion, what happens? You're calling the same function again and again, but maybe for some different parameter. So for each function which has a different parameter, it will have its own individual unique activation record. I mean to say, okay, this is the main part, the main function, and then it will be executed, and then the control will jump to the definition part of F1. Within F1, suppose I pass to F1 the parameter X. Okay, and here also I can store it in a variable, suppose N. Then within this function, I'm calling the same function F1 by passing the parameter, suppose Y. So now this outer function that you can see, this one has one activation record, and this inner function F1, which has been called as a part of recursion, this one also has its own activation record. That means if the parameter is different, like here it is N or X will get stored in N, right? So this parameter is different and this parameter Y is different. So each time the function is called recursively, a new activation record will be there. Because we have seen that just now when I showed you the block diagram, right? We were drawing the blocks like this, then we were jumping here, then again we jumped here, and finally we were returning in the reverse order. So each block stands for each time the function is called. So there are different blocks, so each block has a separate activation record. Each function, whenever it is called, it has a separate activation record. Okay. Now let us discuss about the access link or the access field of the activation record. So control link helps you to return to the appropriate location. Where I need to return is guided by the control link. What about activation link? Activation link helps you to keep a track of all the global or static variables. Now, for the global or static variables are common to all the functions. It is the same for the whole program. Any change made in them will be reflected throughout the program or throughout the function. So these particular global or static variables are same for all the function calls. For that means here we had different blocks for the different function calls, but for all these blocks the global value is same, right? if I make a change in global value x over here, it will be reflected here also. Means the global variable is same for all these function calls. That means I don't need to maintain this value as for individual for each function. This value is common to all function. It is not unique for each function. So this such common data or the values which are global or global static, they will be handled by the access link. Now, before going to that, let me explain one more concept. That is local static and global static. We have seen local variables, static variables, and global variables. Within static, you have another two types, which is static local and static global, or local static and global static. Now, what is the difference between them? See, suppose you have your program over here in this big block. Here you have your global variable, suppose int a. This is a global variable. Then suppose you have certain functions. Within that, you have a static variable. Suppose static int or float or char anything b. So this is a static variable. And then you have, suppose a local variable float c. This is a local variable. So this global variable a is accessible throughout the function. This static variable b is for the function f. It will be considered, its value will be carried forward for each time the function is called. That means the reinitialization will not happen. Once it is initialized, the same value will be considered for the next function call and successive function calls. This float c is a local value, so its effect is noticed within this function f only. Okay, once you call this function, suppose I write whatever the value of c it becomes. Suppose value of c further when you execute it becomes 12. Then it will be for this time only, for the first time when I call the function. Second time when I call the function, its value may change. Okay. Again, or if you are initializing c equal to 13, then first time you call the function, it will be 13. Second time you call the function, again it will be 13. If you make any changes, for each time it will be reinitialized, which is not the case for static variables. I hope you remember this. So we have seen global, static, and local. Now this static which I mentioned over here is a local static. If the static variable is within some function, then it is called as local static. Now there is another thing called as global static. Global static means this static variable will be defined above all the functions or outside all the functions. So here also, suppose you have a memory which is all the block of memory which has been allocated for your program. Then here you will write static int float char anything a. And then you can have the different functions. Suppose f1. Within this, you can have local static variables. You can have local static means here you can write static char c. You can have local variables like float b. and so on. So here also you can have other global variables like int. Here you can have other global variables like int d and so on. But you can also have global static variables. Now what is this? Is a global static variable, whereas this was a local static variable. So what is the difference is, the local static variable is with respect to a particular function. First time you call the function, the value of b will be initialized to suppose 12, and then suppose I do b++, then value of b becomes 13. Second time I call the function, then the value of b will be considered as 13. This initialization to 12 will be skipped. It will not be executed again. The next time, now b is equal to 13, again b++ will happen, b will become 14. Next time I call the function, b equal to 14 will be considered, plus plus will happen, b will become equal to 15. That means reinitialization to 12 is not happening. Similarly, whatever you do for your global static variables, that will be considered throughout the program. Means if a is equal to, if you have a static variable a over here, within f1 you do a++. So since I have not initialized this to anything, by default a is equal to 0, a++ I do, so a becomes equal to 1. Now this a equal to 1 will be considered for other functions also. Suppose you have another function f2, and here if you want to print the value of a, the value of a will be considered as 1, okay, not 0. So it is acting as a global variable here. Your global static variable is nothing but a global variable over here, just like a global variable. So what is the difference between global static and global variable now? Suppose you have created a project, okay, a project which consists of many programs within it. Okay, I'm drawing it at the right side. You have created a project. This project has different programs within it, such as program 1, program 2, and program 3. All these programs are combined so that you can execute your project as a whole. So if you have a global variable, within P1, okay, P1 is a program in which you have a global variable A, then it will be for the P1 only. Suppose you have a global static variable for A, then it will be for, if you have a global variable A, it will be considered for all the functions, all the programs P1, P2, and P3. If you have a global variable B in P2, then this B will be considered for all the programs. But if you have a global static variable Y over here, then this Y will be only for P1. This Y cannot be accessed by the program P2. Okay, that means in a project, the global variable will be for all the programs. The global static variable will be for the corresponding program. It will be not accessed by other programs. Okay, so we can say that the effect of the local static is for the function. The effect of global static is for the particular program, and global variable is for the entire project. Now suppose you don't have a project, that means you have a single program. You have a single program in which you have a, suppose, static int a. This is a global static. Global variable, which is a global static variable. Here what will happen? This particular static variable global static variable is for this function only, for this program only. Okay, for this program only. And here if you have a global variable, suppose you have a global variable int b, it is a global variable, then this global variable is also for your whole program. The only difference comes in when you have a project. Okay, so let me summarize this once again. Local variables are only of one type and they are for the particular function only. They exist only for that particular function. Static variable can be local static or global static. If you have a single program, okay, suppose the program is P1. In that, you can have a global static. Here you can have a global static variable. Here you have some other functions, suppose f, and within f, I have a local static. So this local static variable is for the function f only, but this global static variable will act as a global variable for the program P1. So the global static variable can be accessed throughout the program. It will be the same for the entire program. Same is the case for if you have a global variable over here. You have a global variable. So this global variable will also be common for the entire program P1. So if you have a single program, global static variable and global variable, global static variable and global variable will be common throughout the program. Only local static is for the particular function. But suppose you have a collection of programs which forms a project. You have a program P1, you have a program P2. So what will happen? In P1, you have a global static variable and you have certain local static variable within a function. Okay, local static variable is called local static because it is within a function. So in P1, suppose you have a function f1 and within f1, you can have a local static variable. So this f1 will be having a local static variable which is only for f1 within the P1 program. But this global static variable will be for the entire P1 program. The global static variable will be common for the entire P1 program, and the global static as well as the local static cannot be accessed by the P2 program. But if you have a global variable, if you have a global variable within your P1, then it can be accessed by P2 as well, the same global variable. Okay, so the change between global static and global variable is seen only in case of projects. This whole big block is your project, within which you have two programs P1 and P2. In P1, if you have a global variable, it can be accessed by both P1 and P2. Within P1, if you have a global static variable, then that can be accessed only by P1, not by P2. If you have a local static variable within a function within P1, it can be accessed only by that function F1. Right? So in case of single programs, the global variable and the global static variable is common throughout the program for the single program. And local static is only for the particular function. Okay, local static ka meaning is same. In projects, you have P1 program and P2 program. Global variable within P1 is accessible for both P1, P2. Global static variable within P1 is accessible only to P1 throughout, only for P1 throughout. A local static variable within a function within P1 is accessible only to that function within P1. Okay, you can keep rewinding this and understand the meaning of global variable, global static, local static, and local variable. So the global variable and the global static variable is common throughout the program for a single program. So this can be handled by the access link or the access field of the particular function. Okay, my main motive to explain this was what is handled by the access link. What will be handled? Global variable and global static variable. So what I have told you, link means what? It's a pointer, means it will store some address of some location to which I need to access or return. So suppose you have, what do you have here? You have a global static variable A over here. Okay. So it will be common throughout the program. So it is common for all the functions. So I don't have to maintain it as a unique value for each function. It is common to all functions. So the access link of each function will be able to access such data. That is static variable, global static variable A. So this value A can be accessed by the access link of each function. Now, even if you have a static variable, it is common to the function. So again and again, if the function is called, it is common to all the function calls. So that can be also handled. So global variable, global static, and local static all can be accessed by the access link of each function. So here you have the global static variable A and the local static variable B. See here, access link of the function called F stores the address of B as well as A. So it can access the value of A and B from the memory. Okay. Now in main also you have a static variable B. Now this static variable, which is for the main, and this static variable, which is for the function, they both are different. Because the static variable within a function is a local static variable, which can be accessed only for that particular function for its function calls. So if the static variable B is in F and the same name, that is static variable B, is within main also, they both are indicating different variables B. So the B within the function and the B within the main, both are different memory locations. As you can see here, B can have the address 1000 for the function F, and the B within the main can have the address 2000. So the access link of F function will access the B which is within the F function, and the access link of the main will access the B which is within the main. Okay. So the B of the F function is for the F function, and the B for the main function is for the main function. And that B will be accessed by the access link for F and main respectively. So the B for the F will be accessed by the access link of F, and the B for the main will be accessed by the access link of the main. And the A is a global static, means nothing but global variable for a single program. So the same A will be accessed by F also and main also, because it is global static. It is common for all the functions in your same program. Okay, I hope you understood the use of access link. Since the access link can access the global static, local static, and global variables which are common throughout your program. Okay, means which is same for the function or same for the program. We don't have to maintain as, we don't need it as a unique for the functions. It is common. So we'll control it or access it with the access link of the particular activation record of the particular function. I hope you understood this. So what we understand here, we have certain dynamic part of the activation record and certain static part of the activation record. What does the activation record have? It has the return value, certain information of the microprocessor components like program counter, certain input output information, file handling information, and also control link and access link. Control link will help you to go to the particular location where you need to return after executing the function. Access link can help you to access the global static and local static variables. So the access link stores the values which are common to all the functions or throughout the program. That means this information will be identified by the compiler at the compile time. Whenever a program is getting compiled, this information, since it is common to particular entities, it is common throughout your program, or it is common to the function. So the access link, wherever it points to, that will be identified at the compile time. So it is the static part. Static means nothing but which is same or which is not changing, which is throughout accessible. Okay, that is the meaning of static. Static is nothing but it refers to the compile time. That is, before your program can get executed, it is compiled, and at the time of compilation, we understand that which data is static or global. Okay, if some data is global or static, since it is accessible throughout, it will be known at the compile time itself which value is global, which value is static, and correspondingly the access link can access it. Okay, but the control link, it is dynamic in nature because the parameter that we are passing to the function, that keeps changing. That means each time we call the function, we need to return to some other place. For example, we are calling the function f. Then within this f, we are making some call to the same function by passing some other parameter. Initially from the main, we have passed a parameter x. Now within the function, we will pass from the function, we are calling the same function by passing parameter y. So then we'll jump to the definition part whenever we need to execute it. And then we may call it again for some parameter z. We'll jump to the corresponding definition part and then execute it. And suppose we reach the base case, then we'll keep going backward. That means where we need to go, that is determined at the runtime because memory is allocated to the functions when we are running it. That means each time you execute the program, where we need to return, that location may change. Okay, we need to return within this previous function only, but where in that previous function, the address may change. So this is controlled by the control link. Okay, means control link stores the dynamic information. Right? If we are not doing recursion, then what we are doing? F is calling G, G is calling H. Then H will return to G and G will return to F. So this control link is the dynamic part. Okay, because the parameters are changing each time, it will determine that where we need to return. The address will change. So it is the dynamic part. So access link will get the access, or it knows that where I should point at the compile time. At the compile time, access link will be established. But at the runtime, at the dynamic time, the control link will be established. Okay, so this was about the activation record. And it is necessary to execute any type of function call or even the recursive function call. Now this part was just for your additional knowledge. Okay, when you're writing the program, you don't have to keep in mind what should be my control link, what should be my access link. The compiler automatically will do these things for you internally. You do not have to do them. So as a programmer, if you want to write a program, you don't have to take care of any activation record. You have to just simply call the function within itself and the work will be done automatically. This was just for your additional knowledge that how it works internally. Even if you're not able to learn this part of the memory organization, it's okay. But this was additional information that how it works internally. If you have to just write a program, then you don't have to take care of activation record. Simply call the function within itself. So now we'll execute one program to see how it works. The same program, that is factorial program. What we are doing here, we are initializing, we are declaring a variable int x. Then we are calling the function fact for the parameter 3. So control will jump to the definition part. And then same thing, we'll compare it with 1. If it is 1, we have reached the base case, we'll return 1. Otherwise, in the else part, what will happen? We have to do return n into fact of n minus 1. Okay. So first what happens? Operating system will call the main function. So control will jump from operating system to the main. Then what will happen? Within the main, memory will be allocated to the variable x. Okay, within the main, memory will be allocated to the variable x. and then you need to jump to the particular location. Why? Because you have executed a function call. So the control will jump to the definition part of fact function. So memory will be allocated on the stack for fact function also. Okay. Now memory was allocated for X. Now what about the control link and access link of the activation record of main function? We know that operating system is calling the main. So where the control will return from the main, after executing the main, control will return back to the operating system. So control link of the main indicates or refers or points to a location within the operating system. And access link, what? Why it is null over here? Access link or the pointer, access pointer, it will be null because here, as you can see, we do not have any static, global static, local static, or global variable, right? Access link is only used to maintain the common information, but here there is no static or global variable. So what will happen? Access link will be null for all the functions within this factorial program. Now the control has jumped to the definition part of fact of n. Here n, what is the value? What will be the value of n for the first time call? It will be 3 initially. Okay, initially n will be equal to 3. For this 3, I will compare with 1. Condition is not satisfied. So what will happen? I have to do 3 into fact of 2. So again, my control will jump to the definition part for the parameter 2. So what will happen? So main was allocated the memory. Then my control jumped to this function. So memory was allocated for f when I passed the parameter 3. Okay. And then I did the comparison. 3 equal to 1. I didn't satisfy the if condition. So what happened? I had to perform n into fact of n minus 1. Okay. Now I need to talk about the control link and access link of F3. Now control link of F3, where will it point? Who has called the F function for the first time? Main has called. Okay, this is the first time calling. So control link will establish the link back to the main. I need to return to the main, okay? And access link will be what? Null, because I don't have any global value. Now, within this function call, I have again called the function for f of 2. So again, memory will be allocated for f of 2. Now, what about the control link and the necessary computation will be done? Control link of f2 will be what? It will point to the function who has called it. Who has called it? For the same function with the parameter 3. So I'll return over here. Access link will be null. Access link will be null. Then within this function call for the parameter 2, I will call the same function with the parameter 1. So memory will be allocated for this 1 also. What about control link? It will go or refer to the previous function who has called it. That means for this function with the parameter 2. Access link null. Then again I will do it same thing for the parameter 0. Now what about the control link for the function call with the parameter 0? It will point to the function who has called it. Base case has been reached 0, or in this case what happens? The base case is n equal to 1. Okay, here the base case is n is equal to 1. That means I'll return 1. So after returning when I have to return, I have to go back to the previous function who has called me. That means control link will come. It will help you to reach the control link of f1 function will help you to reach the appropriate location within f2, and memory will be deallocated for f1 function. This memory will be deallocated. Then what will happen? There are no more statements within the function. So I've got whatever value was returned, that into n. I will perform the computation, then I have to return again. So control link will help me to go to the previous. And then here also memory will be deallocated. Then F3, what will happen? I'll perform the necessary computation and then I'll return to my main. So memory will be deallocated for F3 as well. Then I'll execute remaining statements in main, which is the remaining statement, print the factorial. Okay, this statement, I have to print the factorial. So I'll print it whatever the answer is, and then what will happen? I have to return to the operating system, and then the memory will be deallocated to the main as well. Okay, I repeat. Initially, memory has been allocated to main whenever the operating system has called it. Operating system will call main, memory will be allocated, control link of main will be what? To whoever has called it, who has called it? Operating system. Then what will happen? In the main, the function fact3 will be called. So memory will be allocated for this function for the parameter 3. Its control link will point to the main. Then within this function, I'm going to call the same function for the parameter 2. So the control link for this particular function will guide me to the previous one who has called. Then f of 1 similarly, and control link of f of 1 will point to the previous. Once the base case is achieved, I need to go in the reverse order. This is possible by the guidance of the control link. I'll go back, memory will be deallocated. I'll go back, memory will be deallocated. I'll go back, memory deallocated. Then I'll finally reach main. I'll execute remaining things in main, and then memory deallocated for main also, and control will go back to operating system. Okay, you can try this at home as well. So we have understood the factorial program, different representations, how to recursively call it, and also we have understood how to do it with the help of control link and access link. So what we have done till now, we have seen that operating system will call main will call the function for some parameter. Then within that function, I'll call it for some other parameter. Within that function, I'll call for some other parameter. If base case is reached, I'll return some value and go back to the previous one who has called me. Then again, I'll execute remaining things in the previous function, and I will return the particular value. Then again, I'll return and return and return. Okay, once you reach base case, you need to keep on returning backward until you reach the operating system. That is the end of the program. Okay. So how the memory will be allocated? First, operating system will call main. Main will call the function for the parameter 3, then for the parameter 2, and then for parameter 1. If base case is reached, I will return back. And then finally to OS, operating system. So maximum, how many activation records can be there on the stack? 4. 1 for main and the remaining 3 for the recursive function calls. Okay, there can be a question in your interviews or exams that at a time, maximum how many activation records can be present in the stack. So it is always equal to number of recursive function calls or number of calls for the same function. That is fact is called 3 times. So 3 plus 1 for the main. Okay, because main also has to return. From the main also we need to return to the operating system. So activation of main is also necessary. So how many times you call the function, that is 3 times in this case, plus 1 time for the main. Okay, suppose you call the function main. Suppose you call the function main. Okay, this is example number 2. Your OS will call the main. Main will call the function f. Then suppose f will call itself again for some other parameter. It will call itself again for some other parameter. Okay, for different parameters. Then from here, suppose base case is reached, then what will happen? I will return back from here to here, and then again here to here, and then finally to main. Now within main, this was, suppose the main is designed like this. Okay, I'm writing the design of main function over here. Within main, we will call the function f for some parameter. Okay, and within this function, f, there is some recursive calling. Okay, you're calling it again and again. Then finally I reach the base case. Then what will happen? I'll return back to my main. Then within main, next step is suppose another function call. Suppose to f1. F1 also has certain recursion. So F1, what will happen? Now I'm at main. Next step is to call the function F1. So from main, control will go back and call F1 function for some parameter. Then F1 within itself, it will call itself with some other parameter. Then it will again call itself for some other parameter. Finally, if I reach the base case, what will happen? I need to return back, and then finally back to my main. Okay, then the remaining statements will be executed. So what can I say? How many ever times this function is called? How many times this function is called? 3 times. This function again 3 times, plus 1 for the main. Okay, so what will happen? At a time, main will be there in the stack. Then this function f will be called 3 times. So here I am getting that maximum at a time 4 records. Then these 3 records will be deallocated. I'll come back to my main. Then again from main, I need to call the f1 function. So again, there is now 1 activation record. Then 3 times for the f1 function. Here also maximum 4. Suppose this was being called 4 times. Then here 4 records plus 1 for main. So maximum would be 5 and not 4. Okay. Suppose this function was being called, f1 was being called again for some other parameter. Then total number of calls would be 4 plus 1 for the main. So at a time maximum would be 5. Okay. So the maximum activation records at a time on the stack depends on the function which has been called maximum number of times recursively. Okay. Or if you are not doing recursion, what you are doing within main, you are calling the function f. Then what is happening? F is calling g. And then what is happening? G is calling h. And then finally, h will not call anyone. If h does not call anyone, I will execute remaining statements within this, and then I will go back here. I'll execute remaining statements, and then execution of f is complete, so I'll go back here. Then remaining statements in main, and finally back to the operating system. So in this case, what is happening? How the activation records will be? Within your stack, first you will have it for main function. Then main is calling which function? F. Then f is calling which one? G. Okay, these are the activation records. Then G will call f, so h, so activation record of h. Then h will return something, and then G and h, and then to main. So maximum here also at a time you can have 4 activation records. Okay, so number of functions which are called 3 plus 1 for the main. These are the total number of activation records at a time on the stack. Okay, this is just for your additional information. Even if you have not understood this or you don't want to remember, it's fine. Now, what is the difference between normal recursion and the non-recursive function calls? In recursion, what is happening? You're calling the same function again and again. But if you're not calling it recursively, then you're calling the different functions. So in recursion, the calling function and the called function name is the same. That means here if I have a function f1 and it is calling recursively within itself f1, this is your recursion. But if you are not performing recursion, means you're calling the functions normally. For example, the function g1, suppose it is calling a function h1. This is not recursion. Why? Because the function is not calling itself within itself. So this is a normal function call. So what is the main noticeable difference in recursion? Okay, so one more thing. This is called as calling function and this is called as called function. This function has been called. Who is calling it? This one. So this is the calling function which is calling the f1. So this is the called function, the function which is called, and who is calling it is the calling function. So here the name of the calling function and the called function is the same. But here the name of the calling function is g1 and the called function is h1. So in recursion, the names of the functions which are being called and which is calling is the same. But in normal function calling, the function who is calling and the function who is called is different. Okay, this is one main difference. The remaining things are same. Okay, activation record is there for normal function call as well as for recursion function calls. And how we have been able to understand where we have to return and how the memory is allocated, all this time we have been using stack data structure, which you have already seen, right? Push and pop operations, they are done automatically by the system. You don't have to do it for the activation records. Now let us see one question. Write a recursive function to compute the power of a number. Power of a number means, suppose you have a number 5, you are raising it to the power, suppose 2. So 5 raised to 2. You have to compute the final value of this expression. 5 raised to 2 is nothing but 25. So your final answer should be 25 if your number x is 5 and if your power n is 2, then the answer should be 25. Now this calculating the power we have seen by iteration, right? We will multiply the number to itself for the power times. For example, we will perform what we'll perform while power is not equal to 0. In a variable res, we'll keep on multiplying the number. So the power will be finally stored in res variable, right? So suppose power is 2, then we'll multiply the number, then it will be decremented, power will be decremented, power will become 1, we'll multiply the number to itself, then power becomes 0, condition failed. So 2 times we have multiplied, so n square we have got. Okay, we have seen this program already. What we have to do, we have to run the while loop for power times and we have to stop when power becomes 0. And what we have to do in the while loop, we have to keep multiplying the number to itself for power times. Why? Because what is power? Suppose I say 5 raised to 3. It is nothing but 5 into 5 into 5. How many times I have multiplied 5 to itself? 3 times. That is power times. Right? So for power times, you have to repeat the self multiplication. right? So the given problem and its subproblems are of the same nature, so recursion can be applied. Whatever you've written within the while loop or within any loop, that should be written within a function and call that function again and again within itself for the different parameters, right? So let's see here how we have executed it. So first, what we will do, we have passed the base value, that is 5. Suppose x is equal to 5, and then we have passed the power. Suppose power is equal to 2. That means we want to find 5 square. Okay. So initially we'll compare the power with 0. It is not satisfied. Power is 2. We are comparing with 0. 2 equal to 0. Condition false. So what we'll do, we have to compute x into power of the same base, that is 5, and then power minus 1, that is 1. Okay. So let me show you this, like how we can visualize it. So what we are doing, we are calling from the main, right? First time we will operating system calls the main, and then the main will call the particular function. Within your main, you are calling the function power by passing the n value as suppose 5, and you want to suppose 3, and you want to find the suppose a smaller value 2. You want to find its cube. That means this is your n. Here what is the value of n? Here n is equal to 2 and the exponent or the power is equal to 3. Okay. So what will happen? I will jump to the definition part of this power function. What is the definition part of power function? Int n and int p. So n stores which value? 2. And p stores which value? 3. Okay. This 2 gets copied to n and this 3 gets copied to p, right? Now within this, what we are doing, we are executing this thing. We'll check whether it is 0. If it is 0, we'll return 1. Otherwise call x into power of x with p minus 1 parameter, right? So initially, suppose you have passed the value as 2, 3. That means 2 raised to 3. Now what will happen? You will compare the value of power. 3 equal to 1, p equal to 0. So 3 is compared with 0, condition false. So else part, what I have to find? I have to find x or n into p by passing the parameter as which one? Same base, that is 2, with the power 3 minus 1, that is 2. So I will jump to the definition part. And then again I will execute the same function body, but this time I pass the parameter 2 raised to 2. So here again I will check. What I will check? Whether 2 is equal to 0 or not. Condition not satisfied, else part, that means n into the same function p, but this time I'm passing the parameter same base raised to 2 minus 1, that is 1. Now control will jump to the same definition but with the parameters 2, 1. Then I'll again execute. What I have to check? The power 1, whether it is equal to 0 or not. Condition not satisfied, I have to find n into p of base, that is 2, with the parameter 1 minus 1, that is 0. Then again I will jump back to the definition part for the parameters 2 and 0. Again I need to compare 0 equal to 0, condition satisfied, base case has been encountered. So I have to return nothing but 1, right? I am returning 1. So 1 will be returned. Where it will be returned? To this one. So here n was what? This one. 2 into 1. That is equal to 2. This 2 will be returned here. The value of this function call will become 2. And what is the value of n here? This one. It was 2 only. So 2 into 2 happened. What is 2 into 2? Equal to 4. This 4 will be passed here. Value of this function call is 4. What is the value of n here? This one, 2. So 2 into 4, which is nothing but 8. So we have found successfully 2 cube, that is 8. Right? So as you were seeing here, what was happening? You are multiplying to the same number 2 consecutively. To the same 2, you are multiplying something, right? That is what we have seen. So you have successfully computed 2 cube. That is 2 into 2 into 2, and 2 into 2 into 2 is nothing but 8. Okay, so recursion can solve iterative problems also. Whatever is in the loop, you have to put inside a function and call it for the different parameters within itself. Now this is your homework, okay? You have to write a recursive function to calculate the Fibonacci series for 6 terms, n equal to 6. Okay, there are 6 terms over here. You know how to do it by iterations. You have to do it by recursion now. Okay, try it. If you don't get it, in future classes I'll be solving this problem. Now let us solve one more example in which the access link will not be null. Okay, in this example, access link will not be null. So we know that this is our stack region. Okay, this particular thing is our stack. Let me write it over here. Right, we have seen the different regions: heap region, data global or static region to handle the global and static variables, that is this one. Then the stack region, and then the code segment, which stores the actual instructions of your program. Okay, here we are considering the data global or static segment or memory area and the stack area. So here, as you can see, we have a static global static variable. Means it is common throughout your program. Since you have only one program written, you don't have a project. So what happens? This value x will be allocated memory within the data region. Okay. Initially, what is the value of x? I have not initialized, so by default it is 0. Now what will happen? Within the main, I'm calling this function. Okay, this time what I'm doing, I'm not passing any parameter. So let us see what happens. So control will jump from where? From here to here, and I'll execute the statements within this function. What is my first statement? X plus plus less than 3. What is this? Post increment. X is currently 0. So what will happen? I'll consider the current value of x. In post decrement, how post decrement or post increment, what we do? We consider current value, we perform the operation, and then the value of that variable is incremented. So what is x now? 0. Current value of x is 0. So we'll perform 0 less than 3. Okay, and we'll see how it works. So till now what we have seen, operating system will call main. So memory is allocated for the main. Okay, this is for the main. So its control link will point to where? Operating system, and its access link will point to, or it will. Now in this case, the main does not deal with the static variable x, right? Inside the definition part of this main, anywhere can you see the use of x variable over here? Is there use of static variable x over here? No. So the access field or access link of this x, just a minute. Yeah, so access link of this particular main will point to null. Okay, null. Now main is calling this function f, so activation record of f will be there. Okay, what is happening? I'm checking whether x plus plus is less than 3 or not. X is initially 0. X plus plus means now x will 0 less than 3, condition satisfied. So I'll call the function f. Okay, I will call the function f. That means now whatever I had called, its control link was what? To the main, and its access link, it deals with this static variable x. So there is a pointer of the access link. Access link will point to this x. It will provide a guidance to x. Okay, so what we have done till now, main has been called by operating system. It's control link to operating system so that it can return back there when the program is terminated. Its access link will be null because we don't have to access the static variable x from the main. Then main will call the function f. Its control link will provide access to the main, and its access link will access the static variable. Now x was 0, 0 less than 3, condition satisfied. So the function f will be called. Okay, means here the function f is called again from itself, within itself. Its control link will point where? To the previous function call, whoever has called it. And what about it? What about its? And also this x now will get incremented. Why? Because we have used the current value of x, and then afterwards it gets incremented to 1 by plus plus. And then the access link will point to this same x. Okay, then what is happening? X is now 1. 1 less than 3 will be checked. Okay, 1 less than 3, condition satisfied. So I have to again call my function. What about its control link? To the previous whoever has called it. And what about its, and this 1 will get incremented to 2. Okay, and what about its access link? Access link will access this same value x. Now x is equal to 2. So what I will do, I'll again compare 2 less than 3, condition satisfied. Again this function will be called. What about its control link? To the previous whoever has called it. And then this 2 will get incremented to 3. Okay, after using it in your expression, you have to increment it in post increment or post decrement. What about its access link? Its access link will be pointing to the same x. Now x is equal to 3. So since condition is satisfied, I called the function again. Now this time what will happen? 3 less than 3. Condition is not satisfied. That means I'll not call the function again. What I will do, I'll simply print the value of x. That means this if condition is not satisfied, so I will not call the function. I will simply do the next thing. That is, whatever is outside the if. What is outside the if? This printf. So what I will do now, when I have called, what I will do, I will print the value of x. What is the value of x? And one more thing, what I have done, 3 less than 3. I have compared it. Not satisfied. I'll do the next thing. But before that, this 3 will get incremented to 4, right? Because of post increment. And then what will happen? I will print this value of x, which is now 4. So the value of x will get printed 4 at the output. Okay, if this is your output, 4 will get printed. Now I have to return back because the statements within the function are over. So with the help of the control link, I will be able to return back. Okay, control link of this will guide me to the previous. And memory will be deallocated for this one. Then I have come here. Okay, after the if condition, what else I have to execute? This printf. So I'll print the value of the x, that is 4. Okay, now the statements within the function are over. So memory will be deallocated for this one also. And with the help of its control link, I have already jumped over here. Then if condition has been satisfied, after that there is a printf. So I'll print the value of x. What is the value of x? Since it is common to throughout the program, we are accessing only the most recent value. Okay, so 4. And then this memory is getting deallocated. And then I have jumped back from here to here. And then I'll do the printf. I'll print the recent value 4. And then memory is again deallocated for this function. And then finally I'll come back to my main function with the help of control link. Then there is no more statement within main. So what will happen? I'll go back to my operating system. Okay, so the output will be the most recent value of x for how many ever times the function was called recursively. I had called it 4 times and then the condition was violated. So I was able to exit from the recursion and I've printed the recent value 4 times. It is 4444. Okay, I hope you have understood this. You can try this out at home also. Now let us make another change over here. So here what change I have made? I am going to first print the value of x and then I'm going to do this function call. Right? First I'm going to print the value of x and then do this if condition checking. Right? So this is our stack. Initially memory allocated for main. Its control link points to OS and access link is for the null. Okay, null. Then main will call this function f. So memory allocated for f. its control link to main and access link to this X. Now within this function, what I'll do, first I'll print the value of X. Okay, I've called the function. What is the first statement within the function? Print the current value of X. Current value is 0 because I've not initialized. So at the output, what you'll get, at the output, you'll get the current value of X, which is 0. Okay, current value is 0. Then what will happen? You will do this if condition check. X ka value, you'll use current value 0 less than 3. Condition is true. I will call the function again. So when I call this function again, memory will be allocated, control link to the previous function who has called it, and then this X will become incremented to 1, and then access link, as we know, points to the same X. So I've called this function. What is the first statement within the call? I need to print the current value of X. What is the current value of X? The current value of X is 1. Then what I'm doing, I have to do the if condition checking. Current value of X is 1, 1 less than 3. Condition is true. So I have to call the function again. It's control link to the previous, and as we know, access link to the same. And now this X has to be also incremented. It will become 2. Now what will happen? Statements within the function are over, but this f has been called. So I need to print the current value now, 2. And then check for the current value, 2 less than 3. I have to perform this. Condition is satisfied. So what will happen? I'll call this function again. Control link to previous and access link to same the X, and this X also needs to be incremented due to post feature. And then what we'll do, we'll print the, we have called the function, so we'll print the current value 3. Okay, now what will happen? I have to check the if condition again. 3 less than 3, condition violated, so I will not do this function call. The if condition not satisfied, so I will not call the function. Now what I will do, I will return. Okay, because there is nothing, I have not called the function, so recursion is terminated. Recursion, I have exited from it. Okay, it is acting as a base case, so I have to return. So memory will be deallocated for this one, and with the help of control link, I'll come over here. Memory deallocated for this one, control link, I'll come here. Deallocated, I'll come here. Deallocated, I'll come here. Main also, finally no other statements. Deallocated, I'll come back to operating system. So this time output of the program is 0, 1, 2, 3. Last time, due to post increment feature, output was 4, 4, 4, 4. When we were calling the function and then printing. Here we are first printing and then calling the function. So output is the first the actual value 0, 1, 2, 3, and then we were calling. Okay, I hope you have understood these two examples. If not, you can ask me for your doubts. Okay, and try this homework of Fibonacci series. And there are some other variants of recursion which we can execute next time. Okay, so that's all for this lecture. I hope you have understood all the concepts. Thank you.